All right, this is section 7.2 in your textbook, page 342. There is an interesting picture there on page 342. The students are they're measuring the height there, you can see, of a tree. And the way they do it actually is using similar triangles. So you can see they're not actually at the tree itself, they're measuring a meter stick. Okay, so if they can measure the meter stick and figure out the shadow, they can use the fact that the sun is at the same angle, so their shadow is casting the same angle, and they can figure out the height of the tree. Who wants to read that? It's interesting, because it is an interesting way to do it. Did you guys do this in Whitefish Lake?
Yeah,
No,
not
No shadows?
So it was
You
with
did it
the-
directly with the tree.
No, it was like this little thing, like you aim it at the top of it, and
I
then you
think
hold
they
it
give
and
you
it goes
the
in the
It
end.
tells you the angle, okay. All right, who wants to read it? This is a neater, kind of a neater way to do it, yeah.
The geometry of similar figures is a powerful area of mathematics. Similar triangles can be used to measure the height of objects that are difficult to get to, such as trees, tall buildings, and cliffs. They can also be used to measure distances across rivers and even galaxies. Students in the photo are using a meter stick and shadows to measure the height of the tree. How can they do this? What role do similar triangles play in this type of problem?
Okay, good. Who can tell us how are they doing it? How does similar triangles work, what you learned? I know you've only done one section. Luigi?
Basically, they're trying to get the same angle of the shadow. And they know that since the triangles are equal, like proportionally, so they'll just multiply it by the amount of the shadow.
Okay.
So like at the ratio of...
Yeah, the ratio of the side lengths really is what they're looking for, right? So they know the triangles are similar because they know the shadows are cast at the same angle. So they know that angle is the same. They also know that the right angle is the same, assuming the tree goes straight up from the ground. So they have two angles in the triangle that are the same. Therefore, the third angle is the same because of our law of 180 degrees in every triangle. So they know the triangles are similar. If they know the triangles are similar and they measure their triangle, they measure the meter stick is the height of their triangle, and they measure the length of their shadow, which he's doing. They have now a ratio of the two sides. Okay, and so they can relate that to if they know one known of the tree. So maybe they measure the shadow length of the tree. So they don't have to get to the top of the tree, but they measure the shadow length. Now they can solve for the height of the tree. Okay, so that's the idea with similar triangles. All right, so just to review similar triangles again, we're talking about triangles in which corresponding sides are in proportion and corresponding angles are equal. So when I say the sides are in proportion, I mean that the ratio of the sides, so from one triangle to another, are equal. Okay? Again, being careful that you choose the same side. This side is the same as this side. Okay? Being careful with the rotation. All right? So an example of similar triangles, all three of these are similar triangles. Okay? And even though this one has a different rotation and they're all different sizes, even this one as well, they're still similar triangles. How do we know they're similar triangles? Somebody? How do we know they're similar triangles? Yeah? Yeah, the angles. Okay? The angles are all the same. That's how we know it. Okay? And of course, you have these angles given or measured. All right? These are just drawn by me. Scale factor. Okay, this is a very important concept. Scale factor is the factor that relates the corresponding side lengths of two similar triangles. So to get that factor, you can divide any of the two sides. Okay, so as long as you're the longest side over the longest side of the little triangle, let's say, you're going to get that value of k. All right, so any of the sides divided by each other gives you that ratio. So we can see that in these two triangles. We have two similar triangles here. Okay, and we see that when we divide one side over the other, we're going to get a constant value of 3. So 15 divided by 5 is 3, 12 divided by 4 is 3, 6 divided by 2 is 3. Therefore, our scale factor in this particular case is 3, right? Looking at the side lengths here, AB is 2, BC is 4, CA is 5. Each one of those values are multiplied by 3, which is the scale factor. Okay, and that gives you the side length of the other larger triangle. You can think of it in two ways. One, dividing the sides to get the scale factor, or the other, multiplying the smaller side by the scale factor will give you the larger triangle side length. Okay? Yeah?
But if you don't know the scale factor, then you divide.
Yeah, if you don't know what the scale factor is, you can find it out this way. Okay, by dividing the side lengths, once you know that the triangles are similar. Alright? Okay, the other equation that we're going to learn today, and we'll cover it in example 2, is that the area of the larger triangle, so PQR, which is here, is equal to the scale factor squared times the area of the smaller triangle. Okay, and that's really important because it allows us to solve from one area to another very quickly, just knowing the scale factor. Okay, so we don't have to go back to base times height divided by 2 for area of a triangle. We can just go from one area to the other. So this formula is very important. You need to memorize that. You need to know that. Okay, you need to know that the area of the larger triangle is the scale factor squared times the area of the smaller triangle. And we'll prove that in a minute. Okay, so therefore, you can apply the scale factor to find an unknown side length in one triangle if you know the corresponding side length in a similar triangle. Alright, so that's the importance of K. If we know one of the ratios, we can solve for another side length. Okay. Alright, so the first example is on page 343. We're looking for a width of a river, and this is a pretty common problem. I have, Andrew, you want to read?
Sure.
343.
To determine the width of a river, Naomi finds a willow tree and a maple tree that are directly across from each other on opposite shores. Using a third tree on the shore, Naomi plants 2 stakes, A and B, and measures the distance shown. Find the width of the river using the information that Naomi found.
Okay, so we have this made up. We have a maple tree here, sumac there, and a willow tree there. And so she's trying to determine the width of the river. All right, and this is measurements that you guys can make to figure this out too if you're ever stuck in this particular circumstance and need to get to another side of a river. Never know, maybe on a canoe trip. All right, so what she does then is measures these distances. So we have the distance between S and B as 9.3. We have the distance between A and S as 8.4, and B and M as 24 meters. And we're trying to figure out the distance of the river. So any ideas here? What's the first thing we want to try and do? First is to draw the picture. The nice thing about this question is it's drawn for us. What's the next step we want to do? What do we want to establish in this question? What's this whole section about? Yeah, Jason?
The scale factor.
You're right, but before we can do the scale factor, there's something else. We need to determine something first before even there is a scale factor, right? You know? Nicholas?
If the triangles are similar or not.
Excellent. So we want to find out if these two triangles, first and foremost, are similar. Okay? We've created the triangles, right? So we know, what's the first angle we know that's the same? For sure. Yeah, Michael.
It would be the right angle.
Yeah, the right angle. So we know that this is a right angle triangle and this is a right angle triangle. Okay, and the next easiest angle to identify from our angle laws, Jonathan, you remember?
The 45.
No. So you're saying this is a 45?
The other one.
This one?
Yeah.
How do you know it's 45?
Just guessing.
Okay, so we don't need to know what it is necessarily. We just need to know that the 3 angles are the same in the triangle. So can you see any angle laws in between these 2 triangles that might want to tell you one angle is the same as another? Remember the first one we learned? Remember this?
Yeah. Oh, yeah.
So where do you see that?
Between B and
Right here and here, right?
yeah.
Good. So we know we have a right angle and we know we have a similar angle. Therefore, if we have 2 angles in the triangle that are the same, because of our law of triangles, 180 degrees, the third angle has to be the same. Okay, so now we've established that the triangles are similar. That's the key, right? That's the first point that must be done before we can even start talking about scale factor. All right, next thing was the scale factor. We're going to try and determine what that is. So if we look at our formula for scale factor here, we just need to find the ratio of one side over the other. So we're going to look for two sides that we know information about. So on this triangle, the only information we have is this 24. Okay, so definitely that's going to be the ratio, the sides we want to compare. So it's going to be this side to which side on this triangle? Nicholas?
9.3.
Yeah, it's going to be this side, right? Because if you orientate this triangle, think about flipping this triangle up in the same orientation. We're going to see that these two side lengths correspond to each other. Okay? Any questions about that? All right, so we know then that 24 over 9.3 is going to be equal to k. Okay, that's our scale factor. Right? It's determining how much bigger this triangle is than this triangle. Right, so if we divide those two, I think we get
8.4.
8.4.
Oh, no.
No? What's 24
Wait.
divided by 9.3?
2.6.
2.6?
It's a long decimal.
2.6 what?
2.5, like 806.
2.6.
8. All right, let's say that for now. That's our scale factor, 2.58. Okay, once we have the scale factor, now we can just populate this equation to solve for what we need to know. All right, in this particular case, we're asking for the side W. So let's put W over its ratio. So W is the side we're looking for over its corresponding side length, which is 8.4, right? We can see those two sides go together. 8.4. And that's going to be equal to that same scale factor of 2.58. All right, so then our width then becomes 2.58 times 8.4. 21.7. And that's in meters. Any questions about that? So we found our scale factor. It's pretty simple. We took the two known sides that we know, put them over each other, found out our scale factor. The only trick I think then is the only area I can see you guys making a mistake is if you put the ratio side the wrong way when you went to solve for W. If you put 8.4 over W, then you would have solved for the wrong answer of W. Okay, so you have to be consistent. Whatever ratio you determined as your scale factor, again, you usually want to put the larger value over the smaller value. Okay, that's the way you want to do it. Make sure you're consistent when you go to solve for the unknown. Okay, any questions there? All right, that's the one area I can see you guys making a mistake, but then that's pretty simple. All right, example 2. On to area. Let's see over here. It says, what is the relationship between the areas in each pair of similar triangles? So we have a triangle that looks like this. Alright, what is the relationship between the areas in each pair of similar triangles? So let's find out what the areas are. So area of this triangle is going to be base times height divided by 2. So our base is 3 times 4 divided by 2 is 6. And the area of this triangle is 6 times 8 divided by 10. So the area would be 4.8.
Sir, why did you do divided by 10?
Oh, sorry. Good question. I don't know why I did that. My mistake. Base times height divided by 2. Thought that was a weird number, so the answer is actually 24. Right? So we can see that this area is actually what? What's the relationship between the two? Without knowing that formula. Yeah.
4 times the area of the large triangle is 4 times the area of the small triangle.
Yeah, so the larger triangle is 4 times that of the smaller triangle. Okay, good. So that's the first part. Next it says, find the scale factor k for each pair of figures. So B, we want to find the scale factor. So what k is equal to, we always start with the larger side, so we're just going to go one side over another. So 10 over 5 is 2. We could have done any of the corresponding sides, right? 6 over 3 is 2, or 8 over 4 is also 2. Okay, so our scale factor k is 2. And now we want to compare our results in A and B. So we know that it's 4 times larger, our area, and we know our scale factor is 2. So how can we relate how the area changes with the scale factor? And I preluded to this originally, but yeah, Andy?
So the scale factor, like, times itself, multiplied by the smaller triangle to give you a larger triangle.
So say that again, what should I write down? K?
So k squared, or, yeah, k squared times the area of the smaller triangle.
Okay, yeah.
Is equal to the area of the larger triangle.
Yeah, that's right. So we're taking our scale factor of k, we're squaring it to get 4, and then we're multiplying it by the area of the smaller triangle to get the area of the larger triangle. Okay, so this and this are the same thing, right? We've just switched the sides basically. So in other words, you can also say the area of the smaller triangle is equal to the area of the larger triangle divided by k squared. Okay, if we divided both sides by k squared. So whichever one we have given in the problem, whether they give you the area of the smaller triangle or the larger triangle, you can figure out the corresponding area of the other triangle. Okay? That's the important part. So you need to know that formula. You need to know when to use it. Obviously when we're talking about areas. So this relationship holds true for all similar figures. The ratio of the areas of two similar figures is equal to the square of the scale factor. So even if we were talking about rectangles, and we had two similar rectangles, remember, to know if the rectangles are similar, we just have to make sure that all the sides are all the angles are the same. Okay? So if we have two similar rectangles, then we're also going to have that relationship with the areas.
Sir,
Yep.
wouldn't all rectangles be similar then?
Yeah, they'd all have 90 degrees. Yeah. Okay, the last example. The shaded area is to be an industrial zone. Find the area of the industrial zone. Assume that king and queen are parallel and that all streets and the track are straight. So this one's a little bit more involved. So this is example 3. So you can see we have two triangles. Again, we're given, this has 1.4, this says 1.0. And this is 3. Okay, so the first thing you should notice that it's talking about area. It says the shaded area is to be an industrial zone. So this is the shaded area. So we're interested in area. So right away we should think in the back of our minds that this formula is somewhere going to come into play. Okay, if that formula is going to come into play, what do we need to know to use that formula? Ace. Yeah, we want to know the scale factor. Good, first and foremost. So K, can we figure out what K is right away? Well, before we do that, we should first identify that they are similar triangles. Okay, we can do that because we're told that this line is parallel to this line. Okay, so knowing that, we can use Z theorem here to know that these two angles are the same. And then we have opposite angle theorem to know that these two angles are the same. And then we know that finally the last angles also have to be the same. Okay, so we've established that they have the same, that they're similar triangles. Now we're looking for the scale factor. So what do we have information? We have information about this side and information about this side. We want to start with the larger triangle, so we know that this is 3. We know these two are the corresponding sides, so 3 over 1. So our scale factor then is 3. Okay? Once we have the scale factor, which is 3, we want to use this equation. We want to know what the larger area is. So the area of the large triangle is going to be equal to k squared times the area of the small triangle. So we have k, the only thing we do need now is the area of the smaller triangle. And as you can see, it's nicely set up. We're given the height of the triangle here and also the base. So we can find out what this area is. It's just base times height divided by 2. So it's 1 times 1.4 divided by 2. So 0.7 is the area of our smaller triangle. Now finally, we can calculate the area of the large triangle by plugging these two values in. K is 3 squared times 0.7 is equal to 9 times 0.7, which is going to be 6 something?
6.3.
6.3. Okay, any questions? Alright, so then just to recap, you need to know these formulas, right? Our scale factor is just the ratio of one side length over the other, always starting with the larger side length, and then our area formula. So k squared, the scale factor squared times the area of the smaller triangle is equal to the area of the larger triangle. Alright, that's the end of this lesson. You guys can start the homework.